Hi folks, Mr. Long here with a screencast about accumulation and rate functions. So today what we're going to do is start with a rate function that describes, again, snow, because it's really a good way to introduce this idea of accumulation as it relates to calculus, integral calculus specifically, but also derivatives too. So let's take a look at this one. And I think we recognize this rate function as a parabola. So we know that this parabola, it opens up because there's actually a positive value there, and we know it has x-intercepts at 2 and 10. So let's sketch this. We'll do a sketch right here, A, and a sketch in this one would be, it would go through at 2 and at 10, and it would look like this. And from 0, and I think the question later on, it takes us all the way to 12 hours. So you can think of this as sort of from maybe midnight until 12 in the afternoon, when there's massive changes in weather and temperature, perhaps more than is realistic, but nonetheless, it is in this case. So the y-intercept in this case is, we can see that it's going to be negative 2 times negative 10, because 0 minus 2, 0 minus 10. So I get that value. So initially, at the moment you start recording this, the snow is coming down at a rate of 20 centimeters per hour. It stops snowing. The rate is 0 at 2 a.m. And then at 10 a.m., there's another switch. That means that in this area here, it's actually snowing. Then it stops at 2, and in this area between 2 and 10, the snow is melting because it's a negative rate. And by the way, what is that maximum? Let's see here. And I think you know how to do this. I would figure out that the midpoint of 2 and 10 is 12 divided by 2, so 6 is where the vertex is. So I can substitute 6 into the equation, and if I did that, I would end up with 6 minus 2, 6 minus 10, which is 4 and 4, 16. So that vertex is at negative 14 and 6. So that means per hour, that means that snow, the fastest that snow ever melts is at a rate of 14 centimeters per hour. So what are the key sort of things that are happening? We know that initially the snow is accumulated at 20 centimeters an hour, and then the rate slows down and slows down and slows down, so probably the temperature is getting warmer. And then we know at 2 a.m. that the snow stops snowing, and it gets warmer and warmer, and it starts to melt faster and faster until 6 a.m., at which point it starts to probably cool down, and the snow is still melting. It's still melting, still melting, still melting, but slower and slower, and then eventually it gets to another x-intercept of the rate function, and it stops at that time melting, and it switches over to starting to snow, and then the snow will start to accumulate again at a faster and faster rate. So that's what we did there, actually, is part B, describe accumulation from the rate on the graph. So one of the things that we can do here is we can look at how those features create our new graph. So let's actually do that as part of B, to see if we can do a bit of sketching. And this will be a little bit challenging for you, but I think you can do this. So we know some key values are 0, 2, 6, 10. So now this is accumulation. So this is how much snow accumulates on the ground and or melts. So if we look at that, initially there is, because it's accumulation, right? So there's none at the start. And what we know at 2 hours is the snow accumulates for the first 2 hours. So let's think about that. The snow accumulates for the first 2 hours, but at a lower and lower rate, right? It's snowing hard here at 0, and just before it stops snowing, it's not snowing very much at all. and then it switches and it starts to melt. So that means at this location we're going to have some sort of vertex, or what we call a turning point. So let's take a look at that. So I know that the curve gets less and less steep until it gets to 2, and at 2 it turns around. At 2, and then the snow has been accumulating for 2 hours. Between 2 and 10 hours, the snow actually starts to hike. Okay, folks, I just had to pause it for a little bit while I did some extra help. But I'm back, and we're going to continue to work through this. So in terms of sketching this function, this accumulation function, you notice, as we said, that the slope gets less and less steep. And then when we reach 2, we can see that it switches from accumulating snow, accumulating here, and then it goes into melting. So clearly, if it goes from accumulating to melting, it turns. So it turns and comes down. And then it melts until we reach 10 hours. So that means that, and then at that point, it turns again. So it's coming down, it's melting, it's melting, it's melting, and then we reach a turning point at 10 again. So at 10 it goes from, here it's melting, and then anything after 10 is it's starting to accumulate again. So we see that it's going up again, it's starting to accumulate, so we're moving up. So there's a few things to notice there. Let's maybe mark those on. So we have these turning points at 10 and at 2, and what this indicates, these turning points indicate, is that transition from accumulating to melting. And those are, so if you notice here, a maximum on the accumulation curve, or a minimum, right, is represented by an x-intercept on the rate curve. That's a really big idea. So anytime you have a maximum or minimum on your accumulation curve, you get an x-intercept on your rate curve. Now the other thing to think about is, what does this point here mean? That right there, when you have a minimum or a maximum. Well, in our case, that's absolutely the fastest rate at which snow is melting. So if that's when the snow is melting at the fastest rate, let's take a look over here. That seems to occur at 6. What do you notice about the accumulation graph? It's probably when it's at its steepest point, right? Which makes perfect sense. Maximum rate, or minimum, max or minimum rate, will correlate to the steepest part of the graph. Okay, the steepest part of the graph. Good, so there's a lot of big features, or key features there, and important ideas. Okay, so in terms of getting the accumulation function, let's take that on to the next page, and then we're going to look at how much accumulates in the first, or in 12 hours. So what we've got here is our rate function is x minus 2 times by x minus 10, and let's expand that. We're going to get x squared minus 12x plus 20, and that's our rate function, r of x, and yet again here in expanded form. Now to go from rate to accumulation, we remember that accumulation equals what's called the integral of the rate graph, and ours is with respect to x, and the rule that we use is that a of x equals ax to the n plus 1 all over n plus 1, where r of x equals a times x to the n. So in our case, a of x equals the integral of x squared minus 12x plus 20 dx, and now we apply our rule. So a of x will equal x cubed over 3 minus 12x squared over 2 plus 20x. Okay, so that is our accumulation function. That does not tell us at all how much snow there was in the ground at the start of the storm or before it started to melt. It just tells us how much the snow is changing by over a period of hours. And then what we wanted to do is determine, and I'll just do this really quickly so we don't have to go on to another page. What I need to do is to evaluate that. So I need to figure out A at 12 because it said in the first 12 hours. So I know at 0 hours it worked out to, at 0 hours it would work out to 0 because we do not have our y-intercept is 0. So I just figured accumulation at 12 by substituting in 12. And in order to do that, we'd have 12 cubed divided by 3 minus 12 times 12 squared over 2 plus 20 times 12. And I believe the answer to that is on a previous slide. I'm just going to pause it for a second and go back. So that altogether equals negative 48 centimeters. Okay, so negative 48 centimeters, which really does make sense actually when you think about it, because there's so much of that rate curve that's underneath the x-axis. So if we just look at that sketch, it seems to do that, right? And we've got 2 there and 10 there, and this was down at 14, negative 14. So if we look at that from an area perspective, and we did develop this from area under the curve in the beginning, right? It looks as though, change the color on that, the area right here and the area here going out to 12 are much less than the area in this spot, right? So that represents, this part here I'm coloring black right now, that represents a negative, right? It's a negative area because snow is melting, not growing on the surface. So negative 48 centimeters is the net accumulation. So if, for example, there were 100 centimeters at the start of the storm, and well, the 12 hours that includes both snow and melting, there would only be 52 left. Alright, so what I'm going to do now is post some questions that are really very similar to this, except I'm going to turn the quadratic upside down, and you'll still need to sketch the accumulation graph. Good luck when you do that.